So far, I've introduced two gas laws, Boyle's law, which relates pressure and volume, and Charles's law, which relates volume and temperature. I've got two more gas laws to introduce in this lesson, and that's Gay-Lussac's law and then the combined gas law. So Gay-Lussac's law relates pressure and temperature, and specifically it lets us know that pressure and temperature are directly related. And we can actually see that by looking at this drawing here. So if I have a gas that's at 200 Kelvin and a pressure of 1 atmosphere, if I increase that temperature, what happens is the molecules are going to be moving more quickly. So as those gas molecules move more quickly, they're going to collide with the sides of the container more frequently and with more force, which is going to cause the pressure to increase. Notice one thing, and I will address this when I get to the combined gas law, but do notice that the volume is not changing if I'm using Gay-Lussac's law. All right, so just like with Charles's law, which showed a direct relationship between volume and temperature, for Gay-Lussac's law, the formula is going to be the following. P1 over T1 equals P2 over T2. And keep in mind, just like with Charles's law, the temperature must be in Kelvin. All right, so let's look at some examples here. All right, so for example 1, it says a gas system has an initial pressure and temperature of 12 atmospheres, so that's my P1, and a temperature of 27.9 degrees Celsius, so that's my T1. If the pressure changes to 3.74 atmospheres, that's my P2, what will the resulting temperature be in degrees Celsius? Okay, so I'm going to use my formula P1 over T1 equals P2 over T2. I'm going to plug in my P1 is 12.0. My T1, I'm given it in degrees Celsius. So what I need to do, remember to go from degrees Celsius into Kelvin, I need to simply add 273 to my temperature in Celsius. So I'm going to do that right now. So 27.9 plus 273, and I get 300.9. So I'm not going to round this. I'm going to just keep it as it is. That equals my pressure in my second situation, which is now 3.74 atmosphere. So my pressure has decreased, and I'm being asked to solve for my new temperature. Okay, so I'm going to cross multiply. So what this gives me, I have 12.0 times my T2, and that equals 300.9 times 3.74, and that is unrounded 1,125.366. Now I'm going to take 12.0 and divide both sides by that value to get T2 all by itself. Okay, and what I get for my temperature, unrounded, is 93.7805. So 93, I'm going to just round to 93.78. Keep in mind this is in Kelvin, but I want to be in Celsius. So what I now need to do, since I have my temperature in Kelvin, to determine it in Celsius, I simply need to subtract 273 from it in order to get my temperature in Celsius. So I get, for my temperature, negative 179.22 degrees Celsius. Again, you might be tempted to round based on Sig Figs, but keep in mind, because my last step is subtracting, I need to round based on decimal places. So 273 has no decimal places, so I'm just going to keep the 9 there. And so this is just going to round to negative 179, and my units are degrees Celsius. All right, let's look at the next example. A gas system has an initial temperature of 170 degrees Celsius with the pressure unknown. So this is my T1, and it says the pressure for that initial situation is unknown, so that's going to be my P1. When the temperature changes to 1,117 degrees Celsius, so that's my T2, the pressure is found to be 7.77 atmospheres, so that's my P2. What is the initial pressure in atmosphere? So P1 over T1 equals P2 over T2. I don't know my P1, so I'm going to put it up top. I do know my T1, it's 170 degrees Celsius. So I need to take 170 and I'm going to add 273 to that to get it into Kelvin, so I get 443. Okay. That equals my P2, which is 7.77, all over my T2. Well, my T2 is 1,117. I need to add to that 273 to get it into Kelvin, and I get 1,390 Kelvin. And now I can solve this. So I'm going to cross multiply. Okay, so 1,390 times P1 equals, so well, 443 times 7.77. And I get 3,442.11. I'm going to divide both sides by 1,390. And my P1 that I get, unrounded, is 2.476. Okay. Sig Fig wise, remember I'm not going to use 170 to determine Sig Figs. I'm going to use the 443, that temperature in Kelvin. So I have 3 Sig Figs here, 3 Sig Figs here, 3 Sig Figs here. So I need 1, 2, 3 Sig Figs. So this is going to round to 2.48 atmospheres. I'm going to really quickly go back to the first example problem and make sure that both of these answers make sense. So remember, for the first problem, you are decreasing your pressure. So if you decrease pressure, that means your temperature should also decrease. Well, it goes from, my temperature goes from 300.9 Kelvin to 93 Kelvin, or from 27.9 to negative 179. So my temperature is decreasing, which is what I would expect. For the next example, notice I'm increasing temperature, going from 443 to 1,900. So this pressure here, my initial pressure, should be lower than 7.77. And it is, it's 2.48. So that's a nice, easy way to be able to check your math. All right, so the combined gas law. Basically, as you can see from this table, all of my gas laws are derived from one gas law, which is your combined gas law. So P1 times V1 over T1 equals P2 V2 over T2. So you will use your combined gas law when you are changing all 3 of the variables, P1, V1, and T1. If you're not, if 1 or 2 properties of that gas are being held constant, then you'll have one of the 3 laws we've already looked at. So for example, if you're keeping temperature constant, okay, if you get rid of temperature, you've got Boyle's law. If you're keeping pressure the same, you have Charles' law. And if you're keeping volume the same, you've got Gay-Lussac's law. So let's look at 2 examples where we're actually changing all of our variables, pressure, volume, and temperature. So it says a child has a toy balloon with a volume of 1.80 liters. The temperature of the balloon when it was filled was 20 degrees Celsius, and the pressure was 1 atmosphere. If the child were to let go of the balloon and it rose 3 kilometers into the sky, where the pressure is 0.667 atmospheres and the temperature is negative 10 degrees Celsius, what is the new volume? So notice, this is my V1, this is my P1, and this is my T1. Those are my initial conditions. Then my pressure will decrease, so that's my P2. My temperature is going to also decrease because that's what happens when you go up high in the atmosphere. And then I'm solving for my V2. The 3 kilometers is just extra information that you will not actually need to calculate this. So since I'm changing all 3 variables and not just 2, like I did for the 3 other gas laws, I need to use my combined gas law. So P1 V1 over T1 equals P2 V2 over T2. Okay, and now it's just a matter of plugging and chugging. So 1 atmosphere, my volume is 1.80. Remember, my temperature needs to be in Kelvin, so I'm going to take 20 degrees and add 273 to that, and I get 293. Okay, my P2 is 0.667. I don't know my V2, so I'm solving for that. And then I'm going to put that all over my T2, which is negative 10, so negative 10 plus 273 is 263. Now keep in mind, one thing that I haven't really been talking about other than with Kelvin is units. Keep in mind, since my units for pressure, for both of my pressures are atmospheres, no conversions are needed. And I know that my units for volume will be in liters. Since this unit for 1.80 is in liters, then this volume has to be in liters as well. I'm going to cross multiply now. All right, so what that gives me, I'm going to take 293, and I'm going to multiply that by 0.667 times V2, so I get 195.431 times V2, and that equals, so I'm going to take 1 times 1.8 times 263, and I get 473.4. Now I'm going to divide both sides by 195.431. And my volume that I get, unrounded, is 2.422. Okay, Sig Figs, let's look here. 1.00 has 3, 293 has 3, 0.667 has 3, and 263 has 3 Sig Figs. So 1, 2, 3, so 2.42. And my units are going to be liters. So notice there are two counteracting factors in this when we look at what happens to the volume. So when the balloon rises, its volume increases. It goes from 1.80 to 2.42. Why? Well, the pressure is decreasing, which means the volume should increase. But the temperature is decreasing, which would cause the volume of the balloon to decrease as well. Because remember, pressure and volume are inversely related, but temperature and volume are directly related. So clearly the effect of the pressure decreasing is more significant than the effect of temperature decreasing, which is why the volume of a balloon, when it rises up in the sky, will increase until it eventually pops. And keep in mind, when a balloon rises up in the atmosphere, remember, the higher up in the atmosphere you are, the lower the pressure is. All right, let's look at example 2. I have 17 liters of a gas at a temperature of 67 degrees Celsius and a pressure of 88.9 atmospheres. What will be the pressure of the gas if I raise the temperature to 94 and decrease the volume to 12 liters? So since I'm changing 3 variables, I'm using combined gas law. This is V1, this is T1, this is P1, this is my T2, and this is my V2. All right, so my pressure is 88.9 atmospheres. My volume is 17 liters. And my temperature, I need to take 67 and I need to add 273 to that. So I get 340. And I'm going to put 340 point because I just don't want any decimal places, but I want all 3 of these numbers to be significant. Okay. My P2 is what I am solving for because it asks what the pressure is. My volume, it's decreased to 12 liters. Notice my units for volume match up, so I'm good there. And then my new temperature, 94, I need to add 273 to that. And the value I get is 367 Kelvin. Okay? So what I'm now going to do is I'm going to cross multiply. So 340 times 12 times P2 gives me 4,080 times P2. That equals, well, 88.9 times 17 times 367. It's a very large number, 554,647.1. I'm going to divide both sides by 4,080. Okay, and the P2 that I get is 135.9. Keep in mind, 88.9 has 3 sig figs, 17 has 2 sig figs, 340 has 3, 12 has 2, 367 has 3, so I want 2 sig figs. So this is just going to round to 140. Let's figure out what my units are. Well, the units for pressure for P1 are atmospheres, so P2 must also be in atmospheres.